Hello everyone. Today we'll be studying the PN Junction Diode, one of the most basic nonlinear circuit components in electronics. The PN Junction Diode is formed by doping one region with acceptor atoms and forming a p-type semiconductor, and doping another region with donor atoms and forming an n-type semiconductor. This is an example of a pure semiconductor structure where silicon atoms bond with its adjacent silicon atoms with four covalent bonds, thus making a whole silicon structure. Each of these bonds may break down due to thermal agitation and give rise to electron hole pairs. Now, these electron hole pairs are the ones that conduct current in a semiconductor. There are two types of extrinsic semiconductors or impure semiconductors where we introduce impurities to create or increase the number of holes or number of electrons. P-type is used to increase the number of holes. We see here that we've introduced an extra boron atom and we've introduced an extra hole. It can only form three covalent bonds, and thus it introduces a deficiency of electron or a deficiency of a bond. As we can see, with the red arrows, we see that the hole travels from the boron to another silicon bond in number 2, and to another silicon bond in number 3. And we see that the hole movement direction with the red arrow is opposite to the electron movement direction with the blue arrow. As we can see, in the fourth picture, I've summarized how the electron has moved from the lower left to the upper right, back to the boron, whereas the hole has moved from the boron to the upper right, to the upper left, to the lower left. The N-type are much more simpler. They are extrinsically doped semiconductors where we introduce donor impurities, or impurities with one extra electron than the silicon. So it can form four bonds with the adjacent silicons, but the extra electron is completely free, doesn't have to form the bond, so the extra electron can easily roam around the silicon structure, as we've seen with the blue arrows. So to summarize, the p-type semiconductors have majority of their carriers as holes and minority of the carriers as electrons. For n-type, the majority carriers are the electrons and the minority carriers are the holes. The diode is essentially formed by having a p-type and an n-type semiconductor adjacent to each other. The circuit symbol for a diode is as shown below. And as we can see, what the diode essentially does is when a positive voltage is given to it, it creates a shorted state where current is easily able to flow through the circuit. And when a negative voltage is applied to the diode, it creates an open state where current can barely flow through the circuit, and it creates a cutoff condition. So it acts like an electronic switch. Let's take a more in-depth look at diode and what actually happens inside it. So I've created two columns over here, one for holes and one for electrons. For the p-type, there's a lot of holes as the mobile carriers. For the n-type, the holes are the minority carriers, so there's not much. Electrons, n-type has the most electrons and p-type has the least. So clearly, due to a difference in concentration, the carriers would diffuse from a higher concentration to a lower concentration. That means holes would diffuse from the p-type to the n-type, and electrons would diffuse from the n-type to the p-type, as shown with the arrows. And when the holes leave the p-type region, the charges of the impurities are uncovered. So you have negative charges uncovered over here. For the electrons, once the electron goes from the n-type to the p-type, positive charges are uncovered. If we combine the two, we would probably get something like this, where there is a positive charge in the right and the negative charge in the left. And these two are very similar to a parallel plate capacitor, which, as we know, creates a uniform electric field in between the plates, but no electric field outside them. So essentially, this region is what we call the space charge region, and it is created due to the diffusion of carriers and uncovering of space charges between them. Space charge gradually increases with the diffusion of holes and electrons. So let's take a look at what that means. Notice that when the space charge is first created, the electric field is quite small, so the force on these carriers are quite small. So the diffusion direction, on the other hand, the force due to the diffusion is probably much larger than the electrostatic force due to the space charge. As we can see, I've written it over here for the holes and the electrons. But as the space charge increases, more charges are uncovered, electric field increases, the forces start increasing. As we can see, from 1 to 2 to 3, the force is increasing, and at one stage, the space charge reaches a condition where the electric field is enough to create an electrostatic force that is equal and in just enough to negate the diffusion process. That is when the diode reaches equilibrium and there is no more diffusion. Thus, at equilibrium, the diode reaches such a condition where the space charge region has a specific width, and this region is called the depletion region, and the voltage in between, which can be calculated with this formula over here, is called the built-in potential barrier. Now let's take a look at what happens when we apply a positive voltage to this PN junction diode. When a positive voltage is applied, what actually happens is holes are injected from the positive end to the P side, and electrons are injected from the negative end to the N side. Because of this, some of the space charge can be uncovered because the impurities get their holes and electrons back. And when that happens, the space charge width actually decreases. Thus, now that the equilibrium is disturbed, because the equilibrium is disturbed, the holes from the P region can diffuse to the N region, and the electrons from the N region can diffuse into the P region because the electric force is no longer that strong enough to stop the diffusion force. Now that the depletion region is squeezed, there are a huge injection of minority carriers into the respective region. With this diagram, we can see how the holes from the P region is directly injected into the N region. These holes are actually the minority carriers in the N region, right? Same for the electrons injected from the N region into the P region. These electrons, once again, are minority for the P region. And also, once the holes are injected from the P region, holes from the battery are also coming into the P region to replenish the holes that were lost. And same can be said about the electrons. The electrons from the battery in the negative terminal comes to the N region to replenish the electrons that were lost due to injection into the P region. And as we can see, the electrostatic force is very small compared to the diffusion because of the fact that the electric field was reduced. Okay, this diagram should make things a bit more clearer during the forward bias state. What exactly happens? So we can see some of the holes in the P region that I drew, and in the next diagram, we see that the holes are moving forward. The holes are being injected into the N-type region. But wait a second, some of the holes are actually disappearing. Why is that? Because they are recombining with the majority carrier electrons in the N-type region. As they keep moving forward, you can see that they start to disappear more and more as they move even farther and farther away. And at the same time, from the back, you can see the holes are being replenished by the battery, by the positive end of the battery. And if we move forward into the diagram, we see that the holes are moving. As they move forward into the N region, their concentration decreases, but from the back, the holes are always being replenished. And this movement pattern will always continue. But the concentration along at each position is more or less constant. The same can be said about the electrons coming from the N region. The concentration is varying with respect to the distance from the center of the diode, but the concentration is actually not changing with respect to time at any specific position. We can see this more properly summarized through this diagram that I drew. Notice how the minority holes from the minority holes in the N-type region come from the P-type region, right? Because the holes were injected into the N-type region. And notice as the distance from the center or the distance from the space charge region increases, the minority holes are dropping down. The same can be said about the minority electrons. The electrons from the N region were injected into the P-type. They become minority electrons in the P-type region. And from the space charge region, their concentration is also dropping down. And this stays like this. This stays like this. This does not change with respect to time. The concentration always remains like this. However, the concentration is different at each positions of time. That means diffusion is possible. And that's exactly the kind of current that flows through the diode at forward bias state. When the current flows through the entire external circuit, every other place it probably is going to be drift current, as we know for metal conductors. But in the diode, it's diffusion current that acts as the main current factor. And thus, the diode with the positive voltage applied across it will carry a huge diffusion current, and this current is only limited by the external circuit. Let's take a look at what happens when a reverse voltage is applied across this PN junction diode. Well, when a reverse voltage is applied, the battery negative actually provides electrons into the P side. This causes a bit of a problem because these electrons uncover even more space charge because these electrons mix with the impurity holes, and They just uncovered those donor atoms. The same can be said about the positive end of the battery, which provides holes into the N side. So the acceptor atoms are accepting these holes and uncovering even more charge. So the space charge region actually widens. This is a bit of a problem because the electric field is now so much more stronger, and it's practically impossible for any kind of diffusion current to exist in the diode. So we get barely any current. To summarize, the diode acts like an electronic switch where at forward bias or positive voltage, it conducts, creating a shorted path, and at reverse bias, it creates an open circuit where it does not let any sort of current pass. And that's all for PN junction diodes. Thank you.